So the derivation of the kinematics is important. And the reason we care about deriving the kinematics is because we want you, the student, to know that these equations were not just pulled out of thin air, that your teachers didn't just write down a random equation. For those of you that were in class with me in week 1, I wrote an equation on the board. I said, this is the most important equation you will ever see. And then I turned around and told you, I just made it up. But you could have easily solved that equation and got the same answers I did and taken it to an algebra teacher in North Pocono or somewhere else and given them that same equation. And if they had the same input data, they would have gotten the same answer you got, but the meaning of the equation was pointless. We want to make sure that the equations you use have meaning, that they come from someplace and they are not just made up. So we started this year by saying that we needed to know the position of an object, where an object was located. And once we knew that position, we could then know when an object's position changed. Without knowing where position is, then we don't know what change in position is. Once we knew that something's position changed, then we could start measuring and asking and answering the questions that are asked. How fast did it move? How long did it take? Where did it go? So the question of how fast did it move, it gets to if we repeated the process or if somebody else did the same change in position, we could then be able to predict the time component. And so the way we do that is we say that the velocity is the change in position divided by the change in time. And anything moving at a certain velocity covers the same displacement in the same time intervals. It's a definitional equation that answers the question, how long did it take? And how long would the next thing take to travel the same distance? And so displacement and distance if it's a speed. So the question that came up after that was, how fast are we getting faster? And that was acceleration. Acceleration is going to be the change in velocity divided by the change in time. And so the faster we're getting faster. This linear progression of the rate of change of velocity is the rate of change of displacement is velocity, and the rate of change of velocity is acceleration, doesn't end with acceleration. It keeps going. The rate of change of acceleration is called a jerk, and the rate of change of a jerk is called a snap, and the rate of change of a snap is called crackle, and the rate of change of crackle is called pop. Yes, that's right. Your cereal is talking to you. Snap, crackle, pop. And so when we are, you could look that up. You don't have to take my word for that. But we are not going to go down the line of how fast does acceleration change, which is the jerk. Or we're not going to say how fast does the jerk change, that's snap, and how fast does the snap change, and so on and so forth. We are going to focus in on the equations on your screen. These equations connected together help us answer the question of displacement, velocity initial, velocity final, acceleration, and time, the kinematic pieces of data. And so using the equations on the left of the screen and some basic principles of algebra, we are able to come up with 3 unifying equations that connect together 4 of these pieces of data. Here we go. The first kinematic piece of data that we have, which is on the screen here. So the first kinematic piece of data, which we have on the screen here, is referred to as kinematic equation 1. And so kinematic equation 1 starts with our basic understanding of average velocity, that the average velocity of an object is the change in velocity divided by the change in time. We then can rederive this equation by just doing algebra. This is ultimately just algebra in this equation. And what we end up saying is that if I multiply both sides by t, I get this equation, and then if I add the initial velocity to both sides, I get this. and I get the nice clean equation, final velocity is equal to initial velocity plus the acceleration times the change in time. The one piece of this that we need to go back to is that this is average acceleration. The bar means average. And so when the acceleration changes, the average acceleration changes, we have to go and recalculate this particular equation. These equations only work if acceleration is constant. Acceleration must be constant. So an alternative way of calculating deriving the kinematic one is to look at it in terms of graphing. We've been talking about what a graph of velocity versus time looks like and what a graph of position versus time looks like and how we convert between the two. And you can see that here on the screen. We have a velocity versus time graph. The y-axis is the velocity. We have initial velocity, we have final velocity, and the x-axis is time. When we're taking a look at this, what we are seeing is that there is a constant acceleration. The slope of a velocity time graph is acceleration. And so as we look at this, we see that there's a constant acceleration, which is a sign that we can use a kinematic, an algebraic-based kinematic equation to figure out what is going on here. We know from our algebra courses that y is equal to mx plus b. Well, y is going to be where you're located. It's going to be your final velocity. The y-intercept is your initial velocity. And for this particular line, the slope of a velocity time graph is acceleration, and our x component is time. And so when we look at this, we see that we just came up with that first kinematic based on the line that is drawn on the velocity time graph. This is the same equation that we derived on the previous slide. So kinematic 1. Kinematic 2 is going to, and that's kinematic 1 in front of you. Kinematic 2, we are going to start off knowing that there is an alternative way to find average velocity, and that is that when the average velocity is found, it can be found if the acceleration is constant, which we said has to happen in these kinematics, that the acceleration, when the acceleration is constant, the initial velocity plus the final velocity divided by 2, the middle velocity is the average velocity. Let's go back to that graph we just looked at. You can see this here, that when the line has a constant slope, that the average is the number that's right in the middle of that line. That only happens when acceleration is constant. When we look at that along with our initial concept that average velocity is the change in displacement over time, we can put them together, these two equations, set them equal to each other because they're both equal to initial velocity, and we end up simplifying that down, solving for d, simplifying that down into this particular equation. All this is I've multiplied both sides by t, and then I have taken the half and I have pulled it out. So I have 1/2 initial velocity plus final velocity, that's your numerator, times time, which came again from pulling the time over from the other side. We're going to use this equation later, but we're going to manipulate this one right now. So with that said, and with kinematic 1, we know that in kinematic 1, the final velocity was equal to the initial velocity plus at. I could substitute in this equation for final velocity. Remember, we just had final velocity right here, and we can now substitute in this equation, and we get this. From here, it's just pure algebra. Simplifying, we distribute the t through each of the terms. We distribute the half through each of the terms, and what we end up with is this equation, which is what we call the second kinematic. The second kinematic takes the concept of velocity, average velocity, and it takes our first kinematic, which has in it acceleration, and it slams them together to create a new equation. This new equation wasn't just thought up by me or by other physicists, it follows algebraic laws, which means that it is sound in its basic principles that allows us to make accurate predictions, and that it wasn't just man-made. It works because nature says it works. When we talk about an alternative way of viewing this, we take our velocity time graph. This is the same picture we saw in our previous derivation for kinematic 1, but instead of finding the slope of the line, we're going to find the area under the curve. And so what we're going to do is we're going to break this into a rectangle and a triangle. We're going to add them together. The area of the rectangle is going to be the height, which is 0 to v initial, so that's v initial height times time. That would be the area of the rectangle, and the area of the triangle is 1/2 base times height. So the base is time, and the height is the difference between v final and v initial. Now we know, and here it is. This is the height of it. We know that we can then do that substitution, the same substitution we did before, for v final is equal to v initial plus at, the first kinematic. And when we substitute that in for v final, we end up with the same exact equation we previously found, that the equation ends up to be what is on the bottom of your screen. This is called the second kinematic. The last kinematic is the third kinematic. The third kinematic equation starts with the combined displacement equation that we told you earlier to hold on to. Let me go back and I'll show you where that's located. It's right here. It would be this equation here. We start with that. We then are going to use our first kinematic, but this time we are going to solve it for time, and we are going to substitute it in to the displacement equation. What that does is it eliminates time from our equation. So on the screen right now, you have 5 variables. You have displacement, initial velocity, final velocity, acceleration, time. We're going to substitute time in for time. That'll eliminate time and takes us to the 4 variables, which we know in the kinematics only have 4 variables. We will be given 3, solving for the 4th. This leads to, when we do this substitution, the equation that we can see on the bottom of your screen. And immediately you are thinking, oh my goodness, I see something I need to FOIL. And you would be right. We need to use our algebra skills. We need to multiply the initial velocities together, and the outers and the inners, and the final velocities in the last. And when we do that, it's a difference of squares. We end up with the middle terms canceling, the outers and the inners cancel, so we just have the firsts and the lasts, and we then see that we would have the equation on the screen. Now, the one thing that is sort of skipped here in this slide is we pull the 2 over to the other side, and we pull the a. Both the 2 and the a are in the denominator, so we multiply both sides by 2, we multiply both sides by a, and that's how we get 2a over here. And then again, the terms in the middle, we have the difference of squares, and we end up with what you see here on the screen, and the initial velocity squared minus the final velocity. That simplifies itself down. We bring the final velocity to the other side, and we end up with the equation that you can see here on the screen. Okay. If you have any questions, don't hesitate to ask. One big point of this is not that you can do this, it's that you have a deep understanding, then you understand that, the equations didn't just poof out of the air, that they actually come from sound algebraic principles. Have a great day.